Good day, everybody. Today we're going to look at a couple of special trigonometric limits. This is notes number 11. This is a topic that some teachers really get into, and there's a big, long algebraic proof that involves geometry that we could do to prove each of these limits that we're going to talk about today. I think this is a good place where I can cut a little bit of content without sacrificing anything for you guys, and I know we need to do that every once in a while here because we're in a different learning environment right now, and we just can't cover everything we might normally do. So I'm going to make this lesson a bit short. So we have this one limit, the limit as theta goes to 0 of sine of theta over theta. And we have another one, it's kind of a spin-off. It's not as important as the first one. The limit as theta goes to 0 of 1 minus cosine theta over theta. And we're asked to evaluate the limits graphically using a calculator. Okay, so what I'm going to do for the first one is go to my calculator and type in sine of x, close those parentheses, divided by x. I'm going to make sure that my mode is radians. And then for a window, I'm just going to try zoom trig number 7. Okay, we may have even looked at this graph a few days ago when we were doing some limits graphically. So we're interested in what's happening as x gets close to 0, or as theta gets close to 0, whatever we want to call it. And if we look back at the problem and we think about it algebraically, if we were to substitute 0 in for theta, we would have the sine of 0, which is 0 over 0. We would have 0 over 0. So it's indeterminate. So algebraically, we don't arrive at an answer right away. Looking at the graph, I'm going to press trace. Notice that when x equals 0, y is undefined. Okay, that makes sense. 0 is not in the domain of this function. But when x is close to 0, it looks like the y values are close to 1. Same thing on the other side. We could also use the table to show that as x gets close to 0, the y values are getting close to 1. Okay, for the other one, it was 1 minus cosine theta, so I'm going to put that in parentheses, 1 minus cosine x, close those, and then close the whole parentheses around the numerator, divided by theta, so divided by x. I'll go ahead and I'll use the trig window again. Here's what this one looks like. And that's another case where if you were to algebraically just plug in the 0, see if I was just to plug in 0, I would have 1 minus cosine 0 over 0. Cosine of 0 is 1, so I would have 1 minus 1 over 0. So again, indeterminate, 0 over 0. But graphically, it's looking like the value is actually 0. If I press trace, when x equals 0, there is no y-coordinate, but when x is close to 0, the y-coordinate is close to 0. So just graphically alone, we can draw some conclusions here. It's looking like the limit of sine theta over theta as theta goes to 0 is 1. That's the big result of today. That gets used in other trig applications. We just haven't gotten to those yet. And it's also looking like the limit of 1 minus cosine theta over theta as theta goes to 0 is 0. Now, I am kind of a pure mathematician and an algebraist, so I'm used to proving things with algebra and feeling like they're proven. I'm not used to proving things graphically and feeling like they're proven. So can we evaluate these limits algebraically? Well, it turns out for this first one that there is an algebraic proof based on something called the Squeeze Theorem. The Squeeze Theorem is otherwise known as the sandwich theorem. And that's one of those things that I'm just not going to go into detail about. In fact, a moment of science for the Squeeze Theorem. We just have to let that go this year. But I have attached an optional video if you're interested in learning about it. Once you know what the Squeeze Theorem is, you can use it, or some mathematician who was super duper smart and figured out the proof, and then the rest of us just watch it and go, wow, that's cool. We can use it to prove that this limit equals 1. And so I've also attached an optional video with that proof. So if you're interested, you can watch those two videos. Once we've established this first one, we can actually use it to help us prove the second one. So if I want to prove that the limit of 1 minus cosine theta over theta as theta goes to 0 is 0, what I'm going to do is actually I'm going to make use of the conjugate of the numerator. The conjugate of the numerator would be 1 minus cosine theta. Oops, sorry, 1 plus cosine theta, 1 with a plus, 1 with a minus. Those are conjugates. And the reason I do this is because I know that when I multiply conjugates, I get a difference of squares. And I remember that there is a trig identity that has a cosine squared in it. So if we multiply these numerators together using the FOIL method, we get 1 minus cosine squared theta. The insides and outsides cancel. And I'm just going to leave the denominator factored. You've seen me do that in other problems before when I was hoping that something would cancel. Now, I know from my Pythagorean identities that sine squared theta plus cosine squared theta equals 1. So sine squared theta is equal to 1 minus cosine squared theta. So I'm going to do a substitution and rewrite this as the limit as theta goes to 0 of sine squared theta over theta times 1 plus cosine theta. Now, if I break up the numerator and instead of writing it as sine squared theta, if I write it as sine theta times sine theta, you'll notice I can break this into two fractions as well. You'll notice that we have right here the limit that we just said was equal to 1. So if I break this into two limits, which I can do according to those limit laws that we didn't really pay attention to a couple days ago, the limit of a product is equal to the product of the limits. That's probably intuitive. If I break this up, we have this whole thing, which is 1 times, now this one we haven't tried yet to use direct substitution on, so let's try it. Sine of 0 over 1 plus cosine 0. The sine of 0 is 0. The cosine of 0 is 1. So this is 1 times 0 over 1 plus 1, 2. 0 over 2 is 0. 1 times 0 is just 0. So you can prove that second one once you have the other one. Okay, next what I want to do is just go through a few examples real quick. Other problems that we could involve this limit in. The limit as theta goes to 0 of sine theta over theta equals 1. Once we have that established, we can involve it in others. It doesn't have to be a theta, it could be an x or a t or whatever letter you want. So if you look at number 1, you can see we could break this fraction up into 2. We have the limit as x goes to 0 of sine x over x times secant x over 1. See, I just split up the numerator and split up the denominator. So this part right here is 1. And then secant of 0, if we just substitute the 0 in, secant of 0 is the reciprocal of cosine 0. Cosine 0 is 1, so secant 0 is 1. So the answer to this problem is just 1. Now if you look at number 2, it looks a lot like that second limit that we just were looking at on the previous slide, which was limit as theta goes to 0 of 1 minus cosine theta over theta, and that limit was 0. It looks a lot like that, but notice, even though we're using a t, this part looks the same, this part looks the same, but look at this. This is t goes to pi over 2, not t goes to 0. So we're not going to use that limit. It doesn't match. Instead, what do? We try direct substitution. Let's see what happens if we substitute pi over 2 in for t. 1 minus cosine of pi over 2 divided by pi over 2. We're not going to have an indeterminate form. It's not going to be 0 over 0 because the denominator is not 0. Cosine of pi over 2 is the cosine of 90, and that is 0. So we have 1 minus 0 over pi over 2. We have 1 over pi over 2, and that's the same thing as 2 over pi. So there's our answer. Number 3 is kind of like number 1, where we can split this up into two fractions. We have sine of t over t times sine of t over 1. Sine t times sine t is sine squared t. This whole thing right here is just going to be 1. That's that first limit that we were told in the beginning. And then for the other one, we just have sine of 0 over 1. Sine of 0 is 0. So the answer is 0. And then lastly, what if you have something like sine of 4h over h? What are we going to do about that 4? Can we factor it out and just bring it out like that and then make it sine of h over h? Can we do that? Well, the answer is no. You can't factor out a number. Just like if you had the sine of 30, it's 1/2. Is that the same as, well, let me say it this way. What if you had the sine of 3 times 30? Would that be 3 times the sine of 30? Talking about 30 degrees here. Would that be true? Let's see, the sine of 3 times 30 is the sine of 90, and the sine of 90 is 1. On the other hand, 3 times the sine of 30 is 1/2. No, these are not equal. So you can't factor a number outside of a sign, just like if it was inside a radical, you couldn't just bring out the 4. You could do something else, but you couldn't just bring out the 4. So we can't do that, but what can we do? What we can do is we can multiply this fraction by a special form of 1, and that would be, in this case, 4 over 4. The 4 from the numerator I'm just going to bring out to the front because I don't need it. The 4 from the denominator I'm going to multiply by the h. So now we have the limit as h goes to 0 of sine of 4h over 4h times 4. Don't forget about that 4 from the numerator that we brought out. And guess what? If h is getting infinitely close to 0, 4h is also getting infinitely close to 0, so that's still true. Now we have something here. We could call it theta. The same thing here, we could call it theta, and the same thing here, we could call it theta. So this whole limit is just 1. So we have 4 times 1. So the answer is 4. So that's how you can do other trig-related limits using this main trig limit right here. Okay, so that's all I want to say about that. Again, there are optional videos you can watch if you are interested. And for your assignment today, I just want you to catch up on any work that isn't done. Thanks, everybody.